Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, crossing new frontiers to conquer today's challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
I'm Philip Emeagwali. The 9 partial differential equations of modern calculus, called Emeagwali's equations, began as the second law of motion of physics. I encoded that second law of motion into 81 partial derivative terms of Emeagwali's system of equations that governs the multiphase flow of oil, water, and natural gas that was flowing a mile deep and across a production oil field, such as the Oloibiri Oilfield of Nigeria, that was the first oil field discovered in West Africa and discovered in 1956. As a research computational mathematician, I insisted that the petroleum reservoir simulator must obey the laws of physics at all times and simulations. My contributions to mathematical knowledge include the mathematical discovery that the system of 9 coupled, nonlinear, and time-dependent partial differential equations in the calculus textbooks of the petroleum industry we are not equating to the reality within the oil field the partial differential equations represent. For that reason, I invented the 9 Emeagwali's equations that contained 36 partial derivative terms that equated with the 4 physical forces that exist within all production oil fields. Along those lines, I also had to invent 9 finite difference algebraic algorithms that were not constrained by, in inverted comma, dependency, and constrained when executing across my new internet that was outlined by an ensemble of 65,536 commodity off-the-shelf processors that were identical to each other and that were equal distances afar and apart from each other. A necessary condition for making my experimental discovery of the 4th of July of 1989 was that I simultaneously send emails to all 65,536 processors on my new internet, and that I synchronously receive my email replies from all 65,536 processors. That massively parallel processing supercomputer invention took a narrative identity all its own, namely, I, the storyteller, became the story and the subject of school reports. 9 in 10 supercomputer cycles are executed while solving extreme-scaled systems of equations of algebra. On the 4th of July of 1989, the U.S. Independence Day, I experimentally discovered how to finesse my 64 binary thousand identical and commodity processors to email each other and to work together to reduce the time to solution of extreme scale systems of equations of algebra, and to reduce that time to solution from 65,536 days or 180 years on one processor to just 1 day across an ensemble of 65,536 processors. I experimentally discovered how to compute quickly and accurately, and how to make the impossible to solve systems of equations of extreme scale algebra possible to solve, and how to use that new knowledge of massively parallel processing extreme scaled problems in algebra, and doing so to build digital replicas of petroleum reservoirs and the Earth's climate. I experimentally discovered a new supercomputer that encircled a globe and encircled it in the manner the internet encircled a globe, and that could be used to solve never before solved problems in algebra. That new supercomputer is a new instrument that enables the computational mathematician and physicist to answer previously unanswerable questions in the extreme scale algebra that is the recurring decimal in their grand challenge problems. By definition, algebra is the generalization of arithmetic. In high school algebra, the two letters represent two numbers. In the supercomputer algebra that arises from trying to discover and recover otherwise undiscoverable and unrecoverable oil and gas, 1 trillion letters must represent 1 trillion numbers arising from a system of 1 trillion equations of algebra. Those 1 trillion equations are evenly distributed across millions of processors that in turn solves the trillion equations in parallel and solves them by computing 1 million calculations at once. In modern supercomputing, parallel processing is the disruptive technology that displaced sequential processing, a technology that established itself for half a century. Between sequential processing that was experimentally invented in 1946 and parallel processing that I experimentally invented in 1989 was vector processing that was the sustaining technology that yielded incremental gains in the supercomputer speeds of the 1970s and 80s. My world's fastest supercomputer algebraic calculations made the news headlines and entered into the June 20, 1990 issue of the Wall Street Journal. A week later, the computer and information technology writer named Judith Axler Turner wrote in the June 27, 1990 issue of the Chronicle of Higher Education that I, Philip Emeagwali, quote, took on an enormously difficult problem, unquote. That enormously difficult problem that I solved and that made the news headlines was the toughest problem in extreme scale algebra. Judith Axler Turner continued in her Chronicle of Higher Education article that Philip Emeagwali, quote, solved it alone, has won computation's top prize, captured in the past only by seasoned research teams, unquote. I was in the news in 1989 because I experimentally discovered how to reduce the performance abyss between the sequential or the vector processing supercomputer and the massively parallel processing supercomputer. I did not experimentally discover parallel processing by merely tweaking sequential processing codes. I discovered the parallel processing supercomputer from first principles, from the laws of physics, from the partial differential equations of calculus, and from the partial difference equations of algebra. Algebra is the way the supercomputer experienced calculus. I experimentally discovered parallel processing by going back to the laws of physics that were encoded into the system of partial differential equations of modern calculus, that in turn were discretized to yield trillions upon trillions of a system of equations of algebra that I had to solve in parallel. My contributions to computational mathematics are these. I mathematically and experimentally discovered how to compute and solve initial boundary value problems that were previously impossible to solve. I discovered how to execute excruciatingly detailed petroleum reservoir simulations. Such extreme scale simulations in turn enable petroleum engineers to discover and recover otherwise undiscoverable and unrecoverable oil and gas. I discovered how to foresee otherwise unforeseeable global warming, and how to do so by executing extreme scale general circulation models, and how to do so by executing them at a never before seen resolution and executing them across my ensemble of processors that is a new internet and that is a new supercomputer de facto, but that is not a computer per se. The modern parallel processing supercomputer is not the sequential processing computer of the old sense and of the 1980s and earlier. Each modern parallel processing supercomputer is defined by the configuration of the ensemble of processors that outlined it. I invented a new configuration of processors that defined a never before seen supercomputer that I named the cosmic supercomputer, and that outlined a never before seen internet that I described as a hyperbole global network of processors that is described by the book History of the Internet and described as a small copy of the internet and described as the contribution of Philip Emeagwali to the invention of the internet. My knowledge and experience with the with the supercomputer began on June 1974 at the Computer Center at 1800 Southwest Campus Way, Corvallis, Oregon, United States. The computer has changed since it was invented in 1946 and invented as automatic programmable and processing sequentially. But the way we define the computer has not changed. In 1946 and now, we still define the computer as the tool that enables a person to execute the fastest computations. Back in 1974, the prevailing dogma in supercomputing was that parallel processing will forever remain a huge waste of everybody's time. The paradigm shift from serial computing to parallel computing occurred in 1989. There were three reasons I couldn't make my 1989 experimental discovery of parallel processing in 1974. First, I didn't have in 1974 the intellectual maturity across computational physics, across abstract calculus, across large-scale algebra, across extreme-scale computation, and across message-passing communication. I acquired that intellectual maturity during the next 16 years onward of March 25, 1974 of full-time study and supercomputer research. The second reason I couldn't discover parallel processing in 1974 was that I didn't have a global network of 64 binary thousand processors that I needed to use to reconfirm my theoretical discovery of parallel processing. I can only experimentally reconfirm my theoretical discovery across those 65,536 processors. The third reason I couldn't discover parallel processing in 1974 was that the fields of calculus, computing, and email communication grew enough to enable me to do my experiments and do it across a small copy of the internet that's a global network of 64 binary thousand processors. But more importantly, my original inspiration was to discover a new technology, namely a small copy of the internet that emulates a new supercomputer. That new technology, that is a new supercomputer, is a new instrument of extreme scale computational physics that's indispensable in the quest for oil and gas. That's indispensable in foreseeing otherwise unforeseeable global warming. And that's indispensable in vast and sundry problems in extreme scale computational physics. That the fastest supercomputer costs as much as the budget of a small nation is a measure of its wide applications across the sciences and society. Parallel processing is the technological engine that powers both the slowest computer and the fastest supercomputer. My discovery of practical parallel processing earned me the highest prize in supercomputing and made the news headlines in 1989 and was newsworthy because it opened up the new fields of seeking parallel solutions of initial boundary value problems that occurs from mathematics to medicine, from biology to chemistry, and from astronomy to physics. When you are inventing something, that thing is yours. When you've invented that thing, you give that thing to posterity, and that thing is no longer yours. For instance, my experimental discovery of the massively parallel processing supercomputer was the cover story of technical publications such as the May 1990 issue of the Siam News of the Society of Industrial and Applied Mathematics. The Siam News is the flagship bi-monthly news journal of record of the research mathematics community that is 500,000 mathematicians strong.
Insightful and brilliant lecture.